Wish you all a very good evening and welcome to today's evening symposium on airway oscillometry, new perspectives on pulmonary function testing. I am Dr. Sandeep Salvi, and on behalf of the Indian Chest Society, as the Vice President, I welcome you all to this very important webinar. We are very fortunate to have Professor Dr. Brian Lipworth from the Scottish Centre for Respiratory Research from the University of Dundee in Scotland to give us some new insights into a very important diagnostic test called oscillometry, airway oscillometry. During these COVID times, when spirometry, which is still regarded as the gold standard diagnostic test for obstructive airway diseases, because of the potential for aerosol generation, spirometry is not recommended for routine use in today's clinical practice. But there seems to be an alternative test that does not generate the aerosol, and this is the airway oscillometry, the force oscillation technique, or the impulse oscillometer that uses sound waves to measure airway obstruction. So we're going to be talking a lot about this today. And this program that is endorsed by the Indian Chest Society is a very important educational activity to share this knowledge with all the practicing pulmonologists and the budding chest physicians of our country. I will be introducing Dr. Brian Lipworth a little later on at the end of my presentation, and would like to sincerely acknowledge the help of Thorasis and Sheila for having supported this program. What I'm going to do over the next 10 minutes or 15 minutes or so, 15 minutes or so, is to share with you the beauty and the power of breath. Why do we breathe? Why is it essential for us to breathe? What does it actually do to the human body? How has the lung evolved as an organ to fulfill these essential requirements of the human body? I'm going to share with you some very exciting facts and figures. That would be an introduction to the talk by Professor Brian Lipworth. I bring to you greetings from my institute called the Pulmocare Research and Education Foundation, situated in the city of Pune. What is the first thing that we do when we are born? We take the first breath. Isn't that interesting? Because life is defined from the time you take your first breath. Before that, it is not called life. Even when you're in your mother's womb, it is not defined as life. Life starts with the first breath that you take. And what is the last thing that you do before you die? You take the last breath. Life is a period between the first breath and the last breath. Isn't that fascinating that life is equated to breathing? If you stop breathing, you're not alive. If you are breathing well, you're alive. That's how important this very simple process of breathing is to keep us alive. Out of the three basic necessities of life, all of us probably give this the most importance: the food that we eat. We cannot live without food for a few weeks. And if I ask you what is the quantum of food that is necessary for us to keep ourselves fit and well, uh, many of you would give answers in different formats. So some of you may answer in terms of calories, but if I ask you to give an answer in terms of simple weight, how many kilograms of food do you eat every day? Or how much do you need to eat every day to keep yourself fit and well? So the breakfast, lunch, dinner, and maybe an evening snack would account for about maybe up to 2 kilograms of food every day. That is what is required for the human body. The second basic necessity of life is water. And on a daily basis, each one of us needs to drink around 2 to 3 liters every day to keep ourselves fit and well. Now, we have a lot of importance for these two basic necessities of life because we have to work hard for it. We have to work hard for the food that we eat. We have to work hard for the clean drinking water. The third basic necessity of life, which is perhaps the most important one, does not receive the recognition that it deserves: the air that we breathe. And you may perhaps be surprised to know that on a daily basis, each one of us needs to breathe 10,000 liters of air. Isn't that amazing? Compare that with the 2 kilograms of the food and the 3 liters of water. We need to breathe 10,000 liters of air every day. And one of the most important ingredients of air that keeps us fit and well is this molecule called oxygen. You may perhaps not know this, but oxygen provides us with the 90% of our nutritional energy, with just 10% coming from the food that we eat and the water that we drink. Isn't that amazing? 90% of the energy comes from the oxygen that we breathe. If I ask you what is the energy currency of the cell, all of you would certainly answer this as adenosine triphosphate or ATP. And if I ask you how much ATP is produced by the human body every day, many of you perhaps may not know this answer, but you produce as much amount of ATP that is equivalent to your body weight on a daily basis. So if you're weighing 70 kilograms, you would generate 70 kilograms of ATP every day. Obviously, it is used almost instantaneously by the cells, but that is a quantum of energy that is required by the human body to keep ourselves fit and well. And the amazing fact is 90% of this comes from the oxygen that we breathe. What is so special about this molecule called oxygen that it generates 90% of the body's energy? Was a question that was asked to me in a talk that I gave to an undergraduate medical class. And to be honest, I literally had to scratch my head to give the answer. How does oxygen generate energy? Does it burn inside the cell? Does it provide fire? Does it provide heat? How does it generate 90% of the energy? And the answer came from a very simple 7th standard chemistry book. The inner ring of the oxygen molecule has 2 electrons. The outer ring of the oxygen molecule, which should have had 8 electrons, has only 6 electrons, which means that there are 2 empty slots. That means oxygen can accept electrons. And it is this very simple fact, simple principle that helps in generating 90% of the body's energy. The food that we eat that contains carbohydrates, proteins, and fats, the carbon molecules are broken down in the cell. And then all this goes into the mitochondria, where further breakdown occurs and a lot of electrons are generated. Up and until somebody accepts those electrons, the energy that is associated with the food cannot be released. So oxygen acts as the final acceptor of electrons in the mitochondrial electron transport chain. And the moment it accepts the electrons, energy is released in the form of ATP. That is the principle of how oxygen generates energy. Just to show you an example, if you burn 1 molecule of glucose in the absence of oxygen, anaerobic glycolysis, you would produce 2 molecules of ATP. But if you burn the same molecule of glucose in the presence of oxygen, you would generate 36 molecules of ATP. That is the amplifying power of oxygen. Free fatty acids need a lot of oxygen to be used to produce ATP. And in fact, 1 molecule of a free fatty acid, such as palmitic acid, releases about 132 molecules of ATP. But it cannot do that unless there is a lot of oxygen present inside the cell. So that is how oxygen generates 90% of the body's energy. Not only that, but if you look at the structural components of proteins, carbohydrates, and fats, there is always an oxygen molecule in all of these. Why that? Even water molecule contains oxygen. So oxygen is an essential structural component of all the basic necessities of life: proteins, carbohydrates, fats, and even the water that is so very important for us. You may perhaps not be aware that oxygen in the body accounts for 70% of your body weight. So if you are, say, 70 kilograms, 55 kilograms of that would only be because of oxygen that is present in a body. Obviously, a large part of that is because of the water that contains oxygen. And we know that 65% of the body weight is because of water. So, but nonetheless, oxygen is a very, very important component of the human body. If you do not perform any activity and sleep for 24 hours, which I'm sure many of you all do, isn't it? your body would still need to burn 500 liters of oxygen every 24 hours. If you perform your routine day-to-day activities, like what you perhaps have been doing today, going to work, seeing patients, going here and there, your body would need to consume 1,000 liters of oxygen every 24 hours. And if you're an athlete who does regular, you know, tough exercises like running and swimming and jogging, your body would need to burn 1,500 liters of oxygen on a daily basis. And in order to provide this so-called life-giving molecule to the human body, nature has entrusted this responsibility to this beautiful organ called as the lung, situated in the thoracic cage. The main function of the lung is to nourish the body with oxygen. And for that, we need to breathe 10,000 liters of air every day. We all know that 21% of that is oxygen. So out of the 2,100 liters of oxygen that enter inside the lungs soak in around 1,000 liters of oxygen and push it into the circulation so that the other cells and the tissues can be nourished with this life-giving force. If you look at the architecture of the lung, you have essentially two components. You have the ventilation part of the lung, and then you have the perfusion part of the lung. The ventilation part of the lung is the one that pulls in the air in and out on a continual basis for the whole life. The 10,000 liters of air that you breathe, they enter inside the main trachea, and then the trachea divides like the branches of a tree around 23 times until it ends up in the alveoli. Somebody has even counted the number of airways in the human lung very recently, and there are about 40,000 such branching airways in the human lung. As I said, 10,000 liters of air go in and out of this airway branching pattern and ultimately ends up in the alveoli. The alveolus is the portion where the oxygen enters into the blood circulation. There are 600 such alveoli tightly packed inside the thoracic cage. The alveoli have the size of a dodecahedron. That means it has 12 sides, the perfect size, so that you don't leave any space between the alveoli. Nature has made this 12-sided alveoli just like the seeds of a pomegranate. They also have 12 sides, and that ensures that in an enclosed space, the maximum number of seeds or the alveoli that can be fitted in can be done so by having the 12-sided shape. So that's the dodecahedron that the alveoli have. And surprisingly, the amount of blood that flows through the lungs every day is also 10,000 liters. So isn't that amazing? 10,000 liters of air in and out, 10,000 liters of blood in and out of the lungs every 24 hours, only in order to nourish the human body with oxygen. And if you open all the alveoli and spread it across, the surface area would be around 75 to 100 square meters. That's almost the size of a tennis court. That is a surface area that is present inside our own lungs. We have a tennis court size surface area where oxygen diffusion occurs, so that we are all well nourished with this important molecule. Oxygen is transported from the alveoli to the different parts of the body, attached to this protein called hemoglobin that is present inside the red blood cell. And there are some amazing facts over here. Every red blood cell, this tiny red blood cell, tiny microscopic red blood cell, has 300 million hemoglobin molecules stuffed inside it. It needs those 300 million hemoglobin molecules. And for that, it has even got rid of the nucleus. It is one of the only few enucleated cells in the body where the nucleus is absent. And why did the red blood cell get rid of the nucleus? Because it wants to utilize that space to pack in as many hemoglobin molecules as possible. Because this is the molecule that transports oxygen from the lungs to the other parts of the body. So 300 million hemoglobin molecules in each red blood cell. And let me share with you another stunning fact. If you count all the cells in the body, from the tip of your hair to the tip of your toe, every single cell from all organs, the total number of cells comes around 37 trillion cells, 37.2 trillion with a T. Out of these 37 trillion cells, 25 trillion are the red blood cells that are circulating in the blood. Isn't that amazing? Every second, 2 million red blood cells are produced in the bone marrow, and every second, 2 million red blood cells are destroyed. Look at the amount of investment that the human body has made in order to transport oxygen from the lungs to every single cell and tissue in the body. This is the beauty of the entire system that nature has developed. In fact, the major nutrient that circulates in the blood is oxygen. If you take 100 ml of blood and just let it settle down in a test tube, the red blood cells would occupy around 45 ml of that, 45%. That is called as the hematocrit. And that is a portion of the blood that actually transports oxygen. So about 40% or 45% of the blood is actually transporting this very important nutrient to all the cells of the body. And obviously it transports other important nutrients as well. Other than that, the lung also performs some other functions. It encloses the heart, gives it a nice soft covering from all the sides, maintains your acid-base balance. It's a route for water loss and heat elimination, filters of small blood clots, helps generate sound so that I can speak to you what I'm doing now, and so many other things. I mean, those are the so-called non-respiratory functions of the lung. But there is one non-respiratory function of the lung that actually gave me a shock. And this was a paper that was published in Nature a few years ago. The lung as an organ that produces hematopoietic cells. In fact, 50% of the circulating platelets in your blood originate from the lung. Did you know this? There are these hematopoietic cells that are situated in the lung, and the lung is a site that generates, especially the platelets, 50% of the circulating platelets. Uh, if you have to measure lung function, is if your lung is functioning properly or not, you have to ask yourself a few questions. Are the airways patent? Because that's an important component of the way the lung functions. If the airways are not patent, obviously the lung would not be functioning as efficiently as it should. And we all know that diseases that affect the airways that cause narrowing, what we call as obstructive airway diseases, are one of the most common manifestations of lung diseases. So if you have to find an answer to this question, are the airways patent? You need to have an objective test. And these are the tools that will give you the answer. So we know that spirometry is a gold standard diagnostic test for obstructive airway disease. But then we also have something called impulse oscillometry and force oscillation technique, a topic that we're going to cover today. Then we have the body box plethysmograph that also helps you understand patency of the airways by measuring the airway resistance and airway conductance. And then you have the peak flow meter, a very simple tool that gives you some indication of the patency of your airways. Then the next question that you need to ask to measure lung function is, are the airways hypersensitive? You know that asthma is a disease that is associated with hypersensitive airways or hyperresponsive airways. And if you have to measure that part of your lung function, then you have the methacholine challenge test, and then you have the exercise challenge test, and so on. So these are the bronchial challenge tests that will help you find out the answer for this question. Are the airways inflamed? And we know that this is an important component of asthma, where the inflammation is an important part of the process that occurs in the airways. So if you want to find an answer to this question, either you do sputum induction and you get the sputum out and quantify the number of cells and look at the type of cells that are present in the sputum. That will give you an indication of the type of inflammation that is present in the airways. Or you could do a simple test called the fractionated exhaled nitric oxide test. That's a reasonably good test that measures the presence of eosinophils in the airways. What about lung mechanics? Body box plethysmography, PI max, PE max are the tools that will help you find that answer. What is the total area that is available for the gas exchange? You have the body box plethysmograph that will tell you the value of the total lung capacity or the fractional residual capacity, which cannot be measured by spirometry. So that will tell you the answer for this. Or you have the helium washout and the radiology that can help you understand the volume of air that your lungs can have. Is the lung diffusion apparatus functioning well? You have the DLCO test, or the diffusing lung coefficient for carbon monoxide. And then you have the 6-minute walk test, which is an indirect measure of that. So these are all the tools that we need to use in a clinic if we have to find an answer to this question about, are the lungs functioning well? Now, just the three important ones are the airways patent. We have spirometry. Then you have the IOS, or the airway oscillometry, or the FOT. Are the sufficient number of alveoli? You have the body box. Is the diffusion apparatus functioning well? You have the DLCO test. So these are the three basic tests that totally comprise the pulmonary function test. Spirometry has always remained the gold standard diagnostic test for obstructive airway disease. However, the use of spirometry in the whole country is quite small for various reasons. It's not an easy test to perform. It needs the patient should blow very forcefully into the device and for as long as possible. So it's an effort dependent test. And that's a challenge to use in the clinical setting. Requires a lot of good patient cooperation. Doctors do not find it easy to interpret the report. And perhaps it's not a very sensitive tool for diagnosing small airways obstruction. So these are the drawbacks that we have for spirometry, not to mention that it is an aerosol generating procedure. And especially in COVID times, this is a test that is not recommended for routine use in the clinic. And therefore, we need to look for alternatives, tests that do not generate aerosols. Just the last couple of slides to sort of introduce the topic for Professor Brian Lipworth. I have divided the airways into three portions, as you can see in this graph over here. The A is the large airways, the B portion is the medium-sized airways, and the C portion is the small-sized airways. And the reason why I'm showing this is we know that asthma is a disease that can affect all the three portions of the airways. But there is a phenotype of asthma that particularly affects the C portion of the airways, the small airways. And this is called as the small airways disease phenotype, SAD. And recently, there has been a lot of interest in this particular phenotype of asthma that predominantly affects the small airways. And this is a paper by Omar Usmani and Dave Singh from Imperial College. It's a review of literature that tells us what is the proportion of small airways obstruction in patients with asthma. And as you can see here, about half of the asthmatics shows predominantly small airways obstruction. Now, that's the portion of the airways that is very difficult to measure in terms of diagnosis, and perhaps not very easy to even target the small airways in terms of the inhaled drugs. Most of the inhaled medications have particle sizes of between 2 to 5 microns, and very small portion of that actually reaches the small airways. But in clinical practice, we know that asthma can also start in the small airways to start with, but spirometry may not necessarily pick it up. And this particular phenotype of asthma is got a very unique set of clinical presentations. It's difficult to treat asthma. It's a more severe form of asthma that we see. These asthmatics usually have more uncontrolled asthma. They're predominant nighttime awakenings. Asthma that is associated with obesity or exercise-induced or smoking associated are all predominantly associated with small airways, and it seems to be more common in females. So, this phenotype of asthma is getting more recognition, and we need to diagnose these small airways asthma very early and efficiently. COPD is a disease that predominantly affects the small airways, and we know that that's the portion of the lung that is mainly affected in COPD. So if you have to make an early diagnosis of COPD, we know that the ratio that is used to define obstructive airway disease, FE1 upon FVC, may not necessarily be sensitive enough to pick up early COPD. And it only picks up COPD when the disease is a little more advanced. So can we have a diagnostic test that will easily pick up the function of the small airways? Is something that people have been working on this for a long time. And that's where the new device called Airway-Oscillometry as a very important test that has evolved over a period of time. I genuinely believe that it is a test that is going to be more important than spirometry in early diagnosis of asthma, early diagnosis of COPD, and even in evaluating the response to treatment. I see this as the future of lung function testing. And moreover, because it is not an aerosol generating test, so should be an ideal test to perform. With this, I would like to stop my presentation and I would like to invite Professor Brian Lipworth. But before I do that, let me introduce Dr. Brian Lipworth. Very, very fortunate to have him today here. Professor Brian Lipworth is one of the eminent respiratory scientists in the world. He has an index of 84, which is an extremely high. It tells us that he's a very, very one of the topmost respiratory scientists in the world. He's the professor of allergy and pulmonology at the University of Dundee. He heads the Scottish Centre for Respiratory Research and is the clinical professor of allergy and pulmonology at the Nine Wells Hospital and Medical School in Dundee. He has been a visiting professor at the Harvard Medical School, at the University of Florida, and several other very prestigious universities across the world. He's been honored for research excellence by various societies, including the British Pharmacological Society, the Scottish Thoracic Society, the American College of Allergy, Asthma and Immunology, the European Respiratory Society, and so on. He's going to tell us about the clinical applications and future trends of airway oscillometry in asthma and COPD. And I can tell you that I am myself very, very eager to listen to this presentation. But before I really invite him, Professor Lipworth has requested me to just put this note for all the attending delegates. Professor Brian Lipworth is looking for a clinical research fellow starting in the third or the fourth quarter of this year. He's looking for somebody to be with him for 2 to 3 years and hopefully get an MD degree with the University of Dundee. He's hoping that this work will give several high impact publications, and he wants to look at small airway outcomes in asthma and COPD, exactly the same thing that I shared with you in the last couple of slides. So here's a tremendous opportunity for somebody who has an MRCP or an equivalent qualification. And if you're interested, please write an email to him at b.j.lipworth@dundee.ac.uk. So with this, Professor Lipworth, it's a real honor and a privilege to invite you to this very important webinar. And I look forward to it. Thank you very much. Just before Professor Lipworth starts, there will be a question answer session at the end of this. So those of you all who would like to ask questions, please put them in the email that is associated with this. I will read out all those questions at the end, and I'll make sure that these questions are answered by Professor Lipworth, so that all the doubts are clarified. If anybody of you all would like to have access to the publications that Professor Lipworth will refer to in his presentation, please ask us, and especially the Schiller group with Mahua, who is the point of contact, and she will certainly help you get the access to these full papers. So Professor Lipworth, all over to you, and if you could start sharing your slides.
Okay, can you see my screen?
Not yet.
Oh, okay, hold on. Bear with me then. Let me just, hold on. Right, let's have a look where we're going wrong. Share the screen. Okay.
So whilst yes, Professor Lipworth, I think we're getting close.
You got it now?
No. So we can see you opening some files.
Can you see it now?
The presentation is not yet uploaded. No.
No. Okay. All right. Hold on a sec.
I think it will happen.
Yeah, it will. Don't worry. No problem.
Yeah.
Right. Tell you what. Stop sharing. Right. Bear with me.
It came and went.
Yeah. Don't worry. It's okay. I did have it up before, so we know it works. Right. Share screen. Bear with me.
Professor Lipworth tells me it's -2 degrees in Dundee, and so it must be really cold out there.
It is a bit. Right, bear with me while I sort this out. Share screen, and bingo. How about that?
That's right. So if you could.
Right. Yeah, we all good
yes.
to go?
Yes,
Okay.
thank you very much. I look forward to your presentation.
Well, thank you very much. To be honest, Sandeep, I'm really humbled by the kind words, and I really enjoyed your talk. Actually, it was an excellent talk, and I feel very privileged to have listened to that. To be honest, it's a talk that I would love to steal and give to my medical students. It was absolutely excellent. So that was a good start for me anyway, and I learned quite a few new things. So thank you very much. The other thing I would say is that the picture on the slide that you showed looks like my younger brother, but that's another story. It must have been taken a few years ago. So what I want to talk about today is applications and trends in airway oscillometry and asthma and COPD. Can I, first of all, just get rid of some nomenclature, which can be confusing, because we're talking about airway oscillometry, impulse oscillometry, and forced oscillation technique, which are pretty much all of the same thing. And generally, when we're talking about the forced oscillation technique, or FOT, we can roughly divide that into airway oscillometry, AOS, or impulse oscillometry, IOS, which are measured using a similar but different type of technique. So I just thought I'd clarify that in case anybody was confused. I prefer to use the term airway oscillometry because I think it's more descriptive. So I'm briefly going to go over some a brief overview of physiology, which will talk about some of the things which Sandeep has already illuminated. I'm going to talk about how we measure airway oscillometry and what outcomes we can ascertain. I'm then going to break that down separately into asthma and COPD, and then hopefully summarize. So let's get the ball rolling. Well, you've already seen a slide very similar to this from Sandeep, and I just want to reiterate that the airways bifurcate from the trachea at the carina about 23 times. And we can divide that into the larger airways, which are more than 2 millimeters in caliber, and the smaller airways, which are less than 2 millimeters. And in general, we can distinguish between the small and the large airways because that delineates airways from the 8th generation down to the 23rd generation. And as you've already heard, if you unraveled all of the airways from generation 8 to 23, it would be the size of a tennis court. And if you unraveled all of the airways from the trachea down to generation 8, it would be the size of a beach towel. So that just tells you about the importance of the relative importance in terms of the available mucosal surface area of the small airways and the large airways. So if you're only measuring what's going on in the large airways, you're missing a very important part of the overall picture. So how do we assess the small airways? And these are the techniques. This is a review that I wrote in the Lancet Respiratory Medicine about 7 years ago now. And there are several ways which you've already seen. Most of these really are not practical for everyday practice. So, you know, on a regular basis, we're not going to be doing multiple breath nitrogen washout. We're certainly not going to be putting an esophageal balloon down. We're probably not going to be doing high resolution CT scanning or hyperpolarized MRI. We're not going to be putting a bronchoscope down in the clinic, and we're not going to be doing induced sputum. So really the only two methods I think which we could do on a regular basis, and in fact which I do in every patient that walks through my door in the clinic, is firstly spirometry, and secondly they all get airway oscillometry. So if we're talking about airway oscillometry in particular, how is this performed? So this is the device here, and if we then sort of take an X-ray of the device, this is what it looks like. You basically have the patient onto the mouthpiece. There is a vibrating mesh source. Conventional forced oscillation techniques they use a loudspeaker, and a loudspeaker, for example, if you look at the Jaeger master screen device, the loudspeaker is very prone to harmonic distortion, which is not a good thing. This device here, this is the Thorasys tremor flow device. This one has a vibrating mesh, which suffers very little in the way of harmonic distortion. And what it does is that it imparts an oscillation from the vibrating mesh, which is superimposed on the patient's quiet tidal breathing. So this is not an artificial forced expiratory maneuver all the way from total lung capacity to residual volume, which you do in spirometry, which of course is very artificial. This is just normal, quiet tidal breathing. If you can breathe normally, you can do this test. So even children below the age of 5 can do airway oscillometry. It requires very little in the way of cooperation, unlike spirometry. So you superimpose the oscillatory sound wave on top of the patient's normal quiet breathing pattern, and then the measured waveform then gets detected to measure something called the respiratory impedance. And the respiratory impedance is the sum of the resistance and the compliance in the lungs. Some people use the word reactance. You can use reactance and compliance synonymously. So let's see how this is done. So here you have, this is one of our volunteers, and you can see this is a portable handheld device. It's then connected up to a laptop, and then the patient just breathes normally. And importantly, they have to compress their cheeks so that you don't get any artifact from the upper airway in the mouth. And that's it. And then you just breathe normally with a nose clip on, and it takes about 20 to 30 seconds to ascertain the test. This is how you calibrate the device. It's very simple. You put this little calibration device in, which takes very little time, and that calibrates your device. Whereas those of you who are using one of the old-fashioned impulse oscillometers like the Jaeger master screen will know that you need a big 3-liter calibration syringe, and it's a lot of hassle. So what are the advantages of airway oscillometry in real life? Well, it's portable. You can move it from room to room very easy. You can't do that with the master screen device. It's easy to calibrate, as we've said. It's very easy to maintain, much easier to maintain than the master screen. It's very user-friendly for the patient and the clinician. You don't get that horrible thump, thump, thump feeling that you get with a loudspeaker from the master screen device. And crucially, as far as I'm concerned as a clinician and someone who wants to access the data, which is the whole point of the exercise, is it's very friendly in terms of being PC friendly. So you can very easily export the data from this device, which you can't do with the master screen. The only thing you can do with a master screen is get the piece of paper and then manually put that into a database like Excel. So that's why we've actually switched. We used to use exclusively the Jaeger master screen, and we've now switched almost exclusively to using the airway oscillometry device, the Thorasys tremor flow. So what sort of output do you get from this? Well, this is the, if you like, the raw output. And what you're measuring here is impedance. Impedance is simply the pressure in centimeters of water or kilopascals. You can see here, it's divided by the flow. So it's a pressure flow relationship. It's pressure divided by flow in liters per second. So it's either kilopascals per liter per second or centimeters of water per liter per second, pressure flow. And the pressure flow, the impedance, is then plotted against the frequency in hertz. So these are the frequency of the sound waves, which are superimposed on normal breathing. And there are two parts to the impedance, as I've already told you. The first part, which is the in-phase part, is called the resistance, which is denoted by the letter R. The most common thing that we measure is the low frequency resistance, which is R5, resistance at 5 Hertz, and the high frequency resistance, which is measured at 20 Hertz. Lower frequency sound waves can penetrate further and deeper into the lung. So the resistance at 5 Hertz is telling you about the resistance in the whole lung, all the way from the carina down to generation 23, whereas R20, which is the resistance at the higher frequency of 20 Hertz, is telling you about the central airway or proximal airway resistance between the carina and generation 8. So by definition, if you subtract total airway resistance R5 from central airway resistance R20, you will get the peripheral airway resistance. So you'll see this term R5 minus R20 come up in the subsequent slide. Now, not only is there an in-phase or positive part of this waveform, the respiratory impedance, but the respiratory impedance also, if you like, has a sort of a younger brother or an out-of-phase reflection or echo. So think of this as the sort of the ping that you get as the reflective wave. And this interrupted line is known as the respiratory reactance, denoted by the letter X. So this is the out-of-phase component of respiratory impedance. And this, the upper line, the solid line, is the in-phase part of respiratory impedance, resistance and reactance. So with reactance, we can measure, firstly, we can measure the low frequency reactance at 5 Hertz, which is denoted by X5. And this tells you about the stiffness or the compliance in the small airways of the lungs. We can also measure something called the resonant frequency, which is where the reactance line crosses the 0 for the impedance. And that's known as the resonant frequency. The other thing we can measure is the area under the curve between the reactance at 5 Hertz, X5, and the resonant frequencies shown by the hatched area here. And that's also a useful measure of what's going on in the small airways. Okay, so now you understand about the reactance, if we like the compliance or the stiffness, and the resistance. We can go on to look at some data. So this is a patient who came to my clinic with severe asthma. What we did is we did the Airway-Oscillometry reversibility to salbutamol. So here you can see the dark blue line. This is for the resistance. So we're starting with the positive curve. This is pre-bronchodilator, and the lighter blue line is post-bronchodilator. This is the readout you actually get from the thoracic tremor flow machine. And below that, the negative part, this is the reactance or the capacitance, compliance, call it what you like. And in this case, the pre-bronchodilator again is the darker blue line, and the post-bronchodilator is the light blue line. So you can see here that this patient was getting a significant degree of reversibility to inhaled salbutamol. So if we put some numbers on that, when we measured in the same patient at the same time of day, the patient had 16% reversibility for FEV1. When we measured the forced expiratory flow between 25 and 75% of forced vital capacity, known as the FEF25-75, which is a measure of volume-dependent airway closure in the smaller airways, we saw a 15% change. Yet when we measured reversibility using resistance at 5 Hertz, we saw a much bigger change, 48%. In the central airways, it was much less, and that's because asthma is the disease of the small airways, so it was only 23%. When we measured the smaller airways, the difference between R5 and R20, we saw a 75% change. When we measured the area under the reactance curve, that was 79%. And when we measured the reactance at 5 Hertz, small airways compliance, we saw a 58% change. So I think this clearly shows that in patients with severe airway obstruction in asthma, we're seeing really big changes in response to bronchodilators as beta agonists, which you are less likely to detect using conventional spirometry. Even if you're measuring the FEF 2575, you won't get the same type of signal to noise ratio which you get in severe asthma. So then what we went on to do is we compared directly in the same patients head to head in a study where the patients measured simultaneously impulse oscillometry using the Jaeger master screen and Airway-Oscillometry, AOS, using the Thoracis tremor flow. So here you can see this is an Altman blonde curve, looking at the difference between the two devices, the difference between IOS and AOS, the two forced oscillation techniques, plotted against the mean of the post-bronchodilator R5 on the left side and plotted against the mean of the post-bronchodilator reactance curve area on the right side. And we found some interesting observations. The first thing is that when you're looking at the resistance at 5 Hertz, total airway resistance, then as you can see, values for impulse oscillometry tended to be higher than those for airway oscillometry. In fact, there was a 10% mean difference over the whole of these measurements. If you then compare the reactance area, AX, the area under the reactance curve between 5 Hertz and the resonant frequency, then we saw the complete opposite. Whereas impulse oscillometry resistance was 10% higher, in this case, we found that the reactance was 65% higher for airway oscillometry with the tremor flow compared to impulse oscillometry using the master screen. And I think the reason that you're seeing this difference is that this reflects that measuring impulse oscillometry using the Jaeger device is actually under reading. So I think that the airway oscillometry with the tremor flow is giving you a much truer and more accurate reading. And that's down to the way the devices are calibrated. And that's why we have now moved over to using the Thoracis tremor flow. And this has been shown to be the case using models of the bronchial tree that the vibrating mesh with the tremor flow is the much better and more accurate and sensitive device. So what about reversibility in asthma and COPD? Well, here's a paper that one of my recent fellows, Chris Kuo, he looked at reversibility to salbutamol in patients with asthma and COPD. And when you look at the FEV1, you really couldn't distinguish between the asthma and the COPD patients. They both had 8% reversibility to salbutamol. But in the same patients, when you use airway oscillometry and you measure the area under the reactance curve, now you can see what you would expect, that the asthmatic patients had about 2-fold greater reversibility to salbutamol compared to those with COPD. So I think that tells you something really important about the difference between doing a forced expiratory technique to measure the FEV1 and using a tidal breathing method to measure the area under the reactance curve. So what about airway oscillometry and severity of asthma? So this is a patient that this is a study that, again, one of my old fellows, Peter Williamson, published 10 years ago in Lung. And this looks at the respiratory impedance, first as the total airway resistance at 5 Hertz. And you can see that as you go from healthy volunteers to mild to moderate asthma to severe asthma, then you can see there's a progressive increase in the total airway resistance. But here is a really important learning point, because if you look at central or proximal airway resistance as the resistance at 20 Hertz, as you compare healthy volunteers, mild to moderate asthma and severe asthma, there's no difference in the central airway resistance. And I think that teaches very loud and clear that asthma is first and foremost a disease of the small airways. And when you subtract the total area resistance R5 from the central area resistance R20, in other words, R5, R20, you can see that when you go from healthy to mild to moderate asthma to severe asthma, there is a marked increase in peripheral airway resistance. And you see the same thing for peripheral airway reactance, which is the reactance X measured at the low frequency of 5 Hertz. So I think that's a really telling slide, which teaches that when you're looking at asthma, you should really be focusing on the small airways, because that's where most of the disease is. So this is another study where we looked at 378 patients with asthma across British Thoracic Society steps 2, 3, and 4, which are pretty much the same as the GINA steps 2, 3, and 4. The first thing to notice is that when you compare these patients and you look at their FEV1, step 2, 90% mean, step 3, 86% mean, and step 4, 84% mean, there really wasn't that much difference in FEV1. So if you compare step 2 to step 4, there was only a 6% predicted difference in FEV1. If you look at these, the individual data plots for each patient, if you look at the plots for the difference between R5 and R20, the peripheral air resistance, so these are the individuals and these are the means and the confidence intervals superimposed. You can see that even at step 2 patients, the step 2 patients had 65% of abnormal values for R5, R20, and the abnormal value is delineated by this interrupted line here. So despite the fact that these patients had a pretty normal FEV1, you can see that over 60% had abnormal small airway resistance. The figure for step 3 patients was again about 64%, and that jumps up to 70% abnormal values for R5, R20, as you can see here quite clearly in step 4 patients. So this tells you across the BTS treatment steps that measuring airway oscillometry is more sensitive than measuring spirometry using the FEV1. We then went on to do another study. This is from Arvind Manoharan, one of my fellows who's now the lead for severe asthma at the Manchester Institute at Salford Royal Infirmary, is that we found when we screened our database, our NHS and research database, that we found that 302 out of 442 patients with asthma, this was across BTS steps 2 to 4, 60% of these mild to moderate patients had a preserved FEV1. And by preserved FEV1, we define that as more than 80% predicted. In fact, their mean FEV1 was 97% predicted. So nearly over 2/3 of these patients had a preserved FEV1. In these patients who had a preserved FEV1, of those 302 patients, 45% had abnormal airway oscillometry defined by R5, R20. So even in the presence of a normal FEV1, these patients have evidence of persistent small airways dysfunction, nearly half the patients. So don't be fooled if your patient has a normal FEV1, because that does not mean that they have normal airways physiology. So what does it mean if you've got abnormal physiology? Does it mean anything at all? Well, what we did here is that we then linked that same database, and Arvind went on to link it with health informatics. And what I mean by that is each patient in Scotland has a unique community health index, or CHI number, which is a unique identifier. And using that, you can then link them to outcomes like prescribing of the number of salbutamol canisters they get, or the number of bursts of oral steroids. So this enabled us to link in a very sensitive and accurate fashion whether, if a patient has an abnormal FEF25-75 from spirometry, which we defined as being less than 70% of predicted, or abnormal R5-R20 more than 0.07 per kilopascal. By the way, if you want to convert that to centimeters of more water, just multiply it by 10. So that would be 0.07 kilopascals per liter per second, or it would be 0.7 centimeters of water per liter per second. So what we found is that patients who had an abnormal FEF25-75 were twice as likely to require salbutamol use over a 2-year period, and patients who had an abnormal R5-R20 were also twice as likely to require more salbutamol. And the interesting thing is that when you combine those patients with an abnormal FEF25-75 who also had an abnormal R5-R20, so in other words, when both of these parameters were abnormal, then the odds ratio jumped up to 3. And when you look at steroid use, it's a very similar pattern. An increased likelihood of steroid use with an abnormal FEF25-75, the same with R5-R20, but when you combine the two, then you can see the odds ratio, the likelihood of requiring steroids over that 2-year period, so we're looking at long-term control here, jumps up. So the conclusion that we drew from that is that if you really want to fully characterize your patients, and if you want to predict how much reliever use they're using or how many steroid bursts, then you really need to use the combination of spirometry and impulse oscillometry together. I think that's the teaching point from that particular slide. You know, and these weren't mild patients, even though they had a preserved FEV1. I mean, look, their inhaled steroid dose, their mean was 800 micrograms a day, beclomethasone equivalent, and over 42% of them were on long-acting beta agonists. So, you know, it's not like these were mild asthmatics. So how does airway oscillometry relate to asthma control? So in this case, these patients had a mean FEV1, just to calibrate you, of 87%. Their mean beclomethasone equivalent ICS dose was 620. 65% were on LABA, 11% were on LAMA, and 37% were on leukotriene receptor antagonist. So here we have the asthma control questionnaire score. So just to refresh your memory, in case you've forgotten, an ACQ score of more than 1.5 means that you've got poor control, and an ACQ score of less than 0.75 means that you've got good control. So what we found is that when we looked at the reactance area, and we looked at the reactance area of less than 1 versus greater than 1, we found that was highly discriminating in terms of the asthma control questionnaire. So in other words, if you've got non-compliant stiff lungs, you've got a much higher ACQ score. And the difference between the two groups, between the groups who had normal compliance and abnormal compliance, that difference was nearly 1. And the other thing that I should have told you is that the minimal clinical important difference in the ACQ score is 0.5. So that is a clinically relevant difference there in the ACQ score. So having stiff lungs is bad news. If you've got high airway resistance, in this case, we measure the difference between resistance at 5 Hertz at 19 Hertz. It's much the same thing as R5, R20. Give or take 1 Hertz. There's no difference between the two, to be honest. Again, if you look at patients who've got a high peripheral airway resistance, then that also means that they've got much worse control. And the difference there between the low resistance and the high resistance group was greater than 0.5, a clinically relevant difference. We saw the same thing with FEV1, comparing less than 80 and more than 80% predicted. But you can see the significance level wasn't as high. And when we looked at FEF25, 75% predicted, again, we found a difference, but again, it wasn't as significant. So I think that tells you very clearly that measuring peripheral airway compliance as AX or peripheral airway resistance as R519 or R5R20 is very close related to asthma control. Why is the ACQ score important? I'll tell you why. Because the ACQ score is probably the strongest single predictor of whether a patient will have a subsequent exacerbation. And that was shown in the GOLD study by Eric Bateman. So if you're sitting there in the clinic and you want to predict whether a patient's going to exacerbate over the next 12 months, the ACQ score is a very strong predictor. So in other words, this is a marker of exacerbations as well as control. Now, we all know these days that asthma is involved with type 2 inflammation, involving cytokines IL-4, IL-5, and IL-13. So here we have a study in persistent asthmatics with a mean ICS dose of 600 micrograms. These were our patients. Again, it was Chris Cure who analysed the data for me, with a pretty well-preserved FEV1 of 89%. But despite having a preserved FEV1, you can see there was a disconnect in the fact that the ACQ score was 1.41. Remember that threshold for poor control was 1.5. So these patients were not well controlled. Certainly their ACQ was above the 0.75 threshold for optimal control. So let's dig deeper into the data. If your peripheral blood eosinophil count is more than 300, in other words, if you've got significant type 2 blood eosinophilia, you can see that means that you've got stiffer lungs. The difference in AX comparing, these are the means and standard errors comparing 2 and 1, highly significant. So you can see there that having type 2 inflammation means that you have stiffer lungs in the lung periphery. And it's the same thing for the R5, R20. If your eosinophil count's more than 300, then you have a higher peripheral airway resistance. And if your eosinophils are more than 300, then unsurprisingly, you also are more likely to be atopic. You've got a much higher total IgE. And if your eosinophils are more than 300, as expected, as Sandeep's already told you, then you'll have a higher exhaled breath nitric oxide. So we put these two in, the IgE and the FeNO, just to make sure that, you know, we were calibrating the patients correctly, because you'd expect to find that eosinophilia is associated with a higher FeNO and a higher IgE. But what we didn't know, which we thought was interesting, is that if you've got type 2 inflammation, it means that you've got lungs which are more resistive and which are less compliant in the periphery. So we've talked about asthma. I think I've pretty much exhausted that. Let's move on to talk about COPD as well. So what is the archetypical small airway COPD phenotype which you and I see in the clinic? Well, the first thing is these patients have often got hyperinflation, which is evident as an increase in total lung capacity, which you would measure with either helium or nitrogen washout or with the body plethysmograph. Using those same techniques, the patients will have evidence of gas trapping. In other words, they have a high residual volume, and when the residual volume is high, then the forced vital capacity will be reduced. If you measure Airway-Oscillometry, these patients will have a high peripheral airway resistance, and they'll also have a reduced reactance at 5 Hertz and a raised reactance area. And if you were very keen and you did multiple breath nitrogen washout, you would show that they have ventilation heterogeneity in terms of a raised ascena and conductive component. And if you went up to do a high resolution CT scan, you would see they would have increased lucency in terms of increased low attenuation areas. So that's your typical COPD phenotype. So what about airway oscillometry? What's the relationship of resistance R and compliance X to COPD severity? These are probably the best data that I can share with you in over 2,000 patients from this is the Eclipse cohort, which you may have read about. So this is a cross-sectional study, and here you can see they looked at patients in GOLD 2, GOLD 3, and GOLD 4. And the thing I want you to notice here is that although the peripheral airway resistance R5, R20 does increase from 0.15 in goal 2 to 0.2 in goal 3 to 0.24 in goal 4, that increase really isn't that dramatic. So there is an increase in peripheral airway resistance, but it's not really a game changer. But when you look at the peripheral airway compliance, the area under the reactance curve, AX, you can see this really jumps up from goal 2 to goal 3 to goal 4. So if we quantify that, if you look at the percentage difference comparing gold group 4 versus gold group 2, whereas you see a 60% difference in peripheral airway resistance, you see 136% difference in peripheral airway compliance. In other words, you get a much better readout from lung compliance or lung stiffness in COPD than you do from lung resistance. In other words, there's a relative discordance or disconnect between resistance and compliance or stiffness according to COPD severity. So let me just give you a case study, an anecdotal case study. So this is a typical kind of Scottish person who comes to the clinic. Yes, we do have patients who have a 75-year PAC history. That's fairly common. It's a very poor area with large degree of unemployment. It's a 74-year-old man who smoked most of his life from when he was a child. He's now getting breathless up inclines. When we listen with the stethoscope, in keeping with emphysema, he had reduced air entry in his upper zones. His chest x-ray, to be honest, to my eye, was normal. He was starting to get on the slippery slope of hypoxia in terms of his oxygen saturation. Not yet at the level where he needs long-term domiciliary, but certainly on his way. Because he's a smoker, and because he doesn't have type 2 inflammation, his exhaled nitric oxide is low, and he also has low eosinophils as well. Now, you can see here that we did the spirometry at baseline and 15 minutes after salbutamol. And what I want you to notice here, which is not uncommon, is that the pre versus post bronchodilator FEV1 is actually lower. The patient didn't bronchodilate, and the reason for that is that patients with COPD, with severe airflow obstruction, when they do a repeated forced expiratory maneuver, they get effort-dependent worsening in their FEV1, which you can see here. And you see the same, albeit to a lesser degree, with the forced vital capacity. In contrast, we saw marked reversibility in the total airway resistance, 35%, peripheral airway reactance, X5 at 53%, and also peripheral airway reactance as the area under the reactance curve as 79%. So if you were evaluating this patient, you would say, well, there's no evidence of reversibility here, but that's because you're using an unphysiological method, spirometry, which involves dynamic airway closure and volume-dependent airway closure, and that's why you can be missing potential reversibility if you're using spirometry. So I think that's an important teaching case there. The final two slides I want to show you what happens to airway oscillometry when you bronchoconstrict a patient with COPD. So this is like a bronchial challenge test for COPD, in the same way that you would do a methacholine challenge test for asthma. So what we did with these patients were all on ICS LABA, like fluticasone, salmeterol, beclomethasone, formoterol, that kind of thing at baseline. And then we gave them a carvedilol challenge. Carvedilol is a non-selective beta blocker, which is used for the treatment of heart failure. So it's a bit like propranolol, but it's longer acting. So we continued them on the ICS LABA, and then we measured them again after a week while they were taking the ICS LABA in conjunction with the non-selective beta blocker. And then finally, after another week, we stopped the LABA, we continued on the inhaled steroid, and we continued on the non-selective beta blocker. So this was a beta blocker challenge here. at the first time point, and at the second time point, this was a LABA withdrawal challenge, if you like. That's the way I look at this data. And this is Sunny Jabal, who's one of my research fellows who's now moved to Edinburgh. So let me walk you through this, because I think it's really intriguing, actually. If you look at the FEV1, when you give them a non-selective beta blocker, you can see that there's about a 10% fall in FEV1, pretty much what you'd expect. And when you withdraw the LABA, you get a further small decline. It was about 2 or 3% fall in FEV1, so that's there. If you look at the central or proximal airway resistance at 20 hertz, if you give them a beta blocker, nothing happens. If you stop the LABA, nothing happens. So I think that teaches you very clearly that it's really the small airways which are the important part in terms of airway physiology in patients with COPD. I think that's a really important slide there. If you look at the resistance at 5 hertz, the total air resistance, if you beta block them, you can see the airway resistance jumps up by about 30%. And then when you withdraw the LABA, it doesn't really change that much. If you look at the peripheral airway compliance, you can see that that changes to a greater degree than R5. And when you stop the LABA, there's a small increase, but you know, it's not really large. Now, check out what happens with the area under the reactance curve. Oops, my bad. If you look what happens when you give them the beta blocker challenge, look at this. Look what happens to the peripheral lung stiffness. It goes up by 120%. And then after the beta blocker challenge, if you then stop the LABA, you can see the lung compliance changes by another 100%. So again, I think this tells you that there's a relative discordance or disconnect between resistance and compliance in patients with COPD. This is really one of my favorite teaching slides, actually. What about if you give a patient with COPD a bronchodilator? Well, if you look at the total air resistance, if you give them tiotropium, it falls. If you give them a long-acting beta agonist, this was tolbuterol added to tiotropium, it falls again. And if you look at the central area resistance, R20, it doesn't change at all. So again, this is telling you that it's not the central airways which determine the bronchodilator response to a muscarinic antagonist or a beta agonist. It's all happening in the small airways. If you look at the area under the reactance curve, the peripheral lung compliance, then you can see the changes are really dramatic, as in the previous slide. Give them tiotropium, a marked fall in airway reactance. In other words, a large increase in compliance. Reactance and compliance are reciprocal. And then if you give them a long-acting beta agonist, then there's a further fall here. So this tells you that the effects of long-acting bronchodilators in COPD are working in the small but not the large airways. So let's briefly tie up and just briefly compare and contrast spirometry and airway oscillometry. So these are the outputs, which you already know. They've both got a pretty good signal to noise ratio. I would say spirometry is not patient friendly because there's about 20 to 30% of patients who just can't do spirometry, but I've never found anyone that can't do airway oscillometry. And I've already said kids of less than 5 years old can easily do this. If you can breathe normally, then you can do airway oscillometry. Spirometry is not physiological, whereas airway oscillometry is. Spirometry, well, it'll tell you a bit about the small airways if you measure FEF 2575, whereas airway oscillometry is really the only technique which will compartmentalize accurately between the small and the large airways. Cost-wise, well, I guess spirometry is still cheaper than airway oscillometry, but that will change as we move forwards, I guess. They're both portable and they're both FDA approved. So just to wrap up in my final slide, the first point I'd like to make is that airway oscillometry is a physiological, effort-independent, rapid test which can easily measure resistance and compliance. Second point is airway oscillometry using the Thorasys tremor flow is a modern, portable, user-friendly device for the operator and the patient to measure resistance and compliance and to compartmentalize that between the proximal and the distal airways. The third point, airway oscillometry is useful to detect small airways dysfunction. And in the clinic, we mostly use the area under the reactance curve, AX, and the peripheral airway resistance, R5, R20, in asthmatic patients with a preserved FEV1. And you've already seen that if your patients have a preserved FEV1, in about half the cases, they will have undetected small airways dysfunction. Fourth point, the AX and the R5, R20, as you saw from Arvind Manoharan's data and from Chris Kuo's data, they are closely related to asthma control and also crucially related to type 2 inflammation. Fifth point, lung compliance measured as the area under the reactance curve, AX, is more sensitive than resistance as R5 or indeed R5, R20 in patients with COPD. And my final point is that airway oscillometry, I think, should not be used in isolation. I think it should only be used in conjunction with spirometry. I want to emphasize that to fully characterize the physiology of your patients with asthma and COPD. So thank you very much for your attention. And again, just to remind you that if there are any young pulmonologists out there who want to come and train in Dundee for 2 to 3 years, it'll probably be Q3 or Q4. Once we get this COVID thing hopefully out of the way, then if you want to make a preliminary inquiry, then please do that. And thank you very much for taking your time to listen to me on a Saturday, because I know that there is obviously pressure on family time, etc. Thank you again.
Thank you, Professor Lipworth, for an absolutely amazing presentation. Clearly one of the presentations that has clarity of thought. You have wonderful data to support all the statements that you have made. And it also brings about the tremendous clinical application of the use of airway oscillometry in your practice. And I think there's so many brilliant takeaways from your presentation. And I'm sure all the delegates who have been listening to this must have found this very useful. I have been getting a lot of questions. And so if I can get started with that as soon as possible so that we can get, as many clarifications and questions sorted out that have come from the audience. The first question that came was, what is the fundamental difference between an impulse oscillometry and an airway oscillometry technique or a force oscillation technique?
Okay, so the impulse oscillometry technique, firstly, it uses an old-fashioned loudspeaker. Yeah, I mean, this technique was actually first described by Ronald Dubois in 1953 when it used a loudspeaker. Well, technology's moved on now. We have computers, mobile phones, and that's why when Thorasys developed the tremor flow, they started from scratch. So instead of using a loudspeaker, which has got harmonic distortion, they used a much better calibrated method using a vibrating mesh, which doesn't have the same degree of harmonic distortion. So that's really the main difference. And there are also differences you've seen in the way the device is calibrated as well. And that's why we think in terms of signal to noise ratio, harmonic distortion, that we think that the airway oscillometry, AOS, or airflow oscillometry, call it what you like, is the way to go compared to the old-fashioned impulse oscillometry. So let's get this straight. Am I suggesting to you all that if you've already got a Jaeger master screen, you should go and put it in the bin? No. If it's working, then keep using it. But bear in mind that there are other methods available. So if that's what you're using and it's still working, then keep using it until it stops working. I can tell you from personal experience that Jaeger, they're now part of the Viasys healthcare group, they no longer support the master screen, but they don't in the UK. I don't know if they do in India. So when your master screen goes down, that's the end of it. It won't work. So if you are looking to either replace your master screen, or if you've not got any forced oscillation technique, then I would say to you, hand on heart, the best available method, and we've also evaluated other forced oscillation techniques, which I didn't have time to tell you about today, that if you are going to do that, the way to go, for the reasons I've already outlined, would be the standalone thoracic tremor flow for those reasons. But if you've got a machine that's working, keep using it until it stops working, but then you'll find that the company won't support it. And that's exactly what we found recently. They're not interested anymore. They're not developing the device.
Is there any patient discomfort that is observed while performing this test?
Well, we find that with the Jaeger master screen, with the loudspeaker, there is quite a bit of discomfort in terms of the thumping sound of the loudspeaker. Yeah, I mean, on a relative scale of discomfort of 1 to 10, I think, it's like a 2 or a 3, to be honest with you. But patients do say they don't like it. With the vibrating mesh, it's really, really much more patient friendly, and patients hardly notice it at all. And it's much quicker. Instead of, say, a 40 to 60 second signal acquisition period with the iOS device, the Jaeger device, with the tremor flow device, it's about 20 seconds.
Okay. Quite a few other questions. I mean, Brian, you talked a lot about the differences between lung compliance and lung resistance in COPD. Now, this is a game changer for us because, with spirometry, the only concept that we get is this is an obstructive airway disease. There's an airway obstruction, that's all. But are you suggesting that with the airway oscillometry technique, you're not only seeing the airway obstruction, but you're also seeing the lung compliance component of it, which spirometry does not tell you? Because this is something very different, very new.
Yeah, you're quite right. So spirometry will tell you about the airflow obstruction by measuring, the forced expiratory ratio, the ratio of FV1 to FVC. Spirometry, to be fair, it will tell you about gas trapping, because the degree of reduction in the forced vital capacity from predicted normal is directly related to the degree of gas trapping in terms of residual volume. So I've already said, when your residual volume is high, you get a proportionate reduction of the forced vital capacity, which you don't usually see in asthma. In asthma, most patients with asthma, unless they've got airway remodeling, they don't have gas trapping and the forced vital capacity is preserved. So you will get some evidence of small airways disease in spirometry in terms of the reduction of the forced vital capacity. And actually, if you do a relaxed vital capacity, a slow vital capacity, or relaxed, call it what you like, in COPD, and then you subtract the relaxed vital capacity from the forced vital capacity, that will also give you a reasonable index of the amount of gas trapping as well. We've published data on that before. But I digress there. The point is that the only technique really which will tell you about lung compliance or lung stiffness is using airway oscillometry to determine either the reactance at 5 Hertz or the area under the reactance curve AX. And I think that's something which is really, really telling. And if you look at the response to treatment, as you've already seen from the bronchodilator studies with tiotropium and tolbuterol, or the bronchoconstriction studies with carvedilol and LABA withdrawal, that really does show you that you're getting deflation of the lung when you're giving bronchodilators, which you really don't pick up to the same degree with spirometry. And that's why that you can give someone, a LABA-LAMA, for example, in COPD, and you measure their FEV1, it doesn't really change very much. And the patient comes back to see you and says, doctor, it's been a complete game changer. I can now walk a mile, whereas before I could only walk 400 yards. And you look at your chart and you say, well, your FEV1, it's gone from 40% predicted to 42% predicted. But when you look at the AX, you'll find in that patient, the AX will change by 40 or 50%. And the reason is that when you're giving the long-acting bronchodilators in COPD, you're deflating the lung So you're making the lungs less stiff, and that means that the patient can breathe at a better mechanical advantage with deflated lungs. And that's something that you can only pick up. And I think it's really useful because when the patient comes back to me, I can say to them, well, you know, that's really interesting because I can see that your lung stiffness has improved by 40%. And the patients really appreciate being told that, you know, your lungs are less stiff, you're breathing at a better mechanical advantage. And if you give that positive feedback to patients, you know what? They're more likely to adhere to their treatment in the long term if you give them positive reinforcement. You know, it's like the carrot and the stick. If you give a dog a treat while you're training it, it's likely, you know, to give you its paw and sit down. And it's the same thing with patients. Patients like positive reinforcement. So if you say to a patient, I've given you this treatment and it's reduced, you know, it's improved your lung compliance. Well, I use the word lung compliance. I use the word lung stiffness because they understand that. Then they go, oh, right. Well, I think, you know what? I think I'll continue taking that treatment because I can see what good it's doing me. And you can actually show them the tracing on the area under the reactance curve. And if you trace around it, you can actually show them how much they've improved, which is a really good visual to a patient to reinforce why it's important they should take their treatment. So it's a very good educational tool for patients.
Absolutely brilliant, Brian. I think, so I'm looking at this as a completely new application in clinical practice. I mean, the whole understanding of obstructive airway disease is only obstruction, whereas this is giving you a completely new dimension to look into. And that has perhaps a lot more clinical application than what just looking at the obstructive elements as well. Dr. Murli Mohan, who worked with you quite a few years.
Oh, right.
Yeah. So he's asked 2 questions.
Actually, if Murli's there, I'll tell him that I still have the tie, and it's in my wardrobe there. I still have the tie which he kindly gave me once when he came back from India. I'm sure he's smiling now, but I still have it, wear it. So
I'm sure he's smiling.
With you again today. Yeah.
So he said, great to hear from you again. 2 questions for you in the COVID pandemic. 1, is airway oscillometry safer than spirometry?
Yes.
Okay, good.
Yeah, it's not aerosol, Jerry. It's tidal breathing. Yeah.
Okay. 2nd, would the data you show make a stronger case for use of extra fine particle corticosteroids in patients with COPD? So do you think it's a game changer in terms of the whole pharmacotherapy could potentially change because of the fact that you're now talking about small airways obstruction in both asthma and COPD. And we know that the standard inhaled corticosteroids have a particle MMAD of 2 to 5 microns. They may not necessarily be reaching the small airways in sufficient amounts. Do you think that this whole thing could change or revolutionize the way we treat COPD with inhaled steroids or asthma, the small airways disease phenotype of asthma?
Well, I didn't have the time to go through that today. Otherwise, I'd still be talking. And maybe if the Indian Chess Society wants to invite me back again, I'd be happy to give a separate talk looking at the impact of different treatments on small airways outcomes. So, Murli, yeah, the answer to that is definitely yes. So what we've shown, and others have shown, is that if you compare conventional particle formulations, for example, of inhaled steroid in asthma, with a particle size with an MMAD of say 2.5 to 3 microns, and you compare that to an extra fine particle formulation of inhaled steroid with an MMAD of 1 micron, then you get marked improvements in small airways outcomes. And it's actually also been shown with bronchodilators as well. Arvind Manoharan, one of my previous fellows, who's now in Manchester at the Salford Lung Centre, he published a seminal paper in the Journal of Allergy and Clinical Immunology a few years back, comparing bronchodilators with different particle size, and again, showed that there was a marked improvements in both resistance and compliance in asthma. So look, if you forget all of that, if you said to me, and I say to my patients, when my patients come back and they haven't responded to a coarse particle inhaler, whether it be an ICS or a LABA, and I say to them, look, I'm going to switch you to an extra fine particle formulation of an ICS or an ICS lather. And the way that I explain it to them is that if you compare the size, if I tell them it's 2 microns against 5 microns, they don't understand that. So what I say to them is that I'm going to change the formulation, and instead of delivering, particles the size of a football, I'm going to be delivering particles the size of a golf ball. And that means the particles are going to penetrate deeper into the lung. So assuming the cost is the same, why would I use a formulation of inhaled steroid or ICS LABA, which only reaches part of the lung, part of the inflammatory wallpaper? It would be as stupid as inviting someone to come in and decorate my study. You can't see my study because I've got a background, because it's a horrible mess. It's not as tidy as yours, I'll give you that. But if I said to a decorator to come in and said, could you decorate the wall? And he came in, and a week later I came back to inspect the work. And I said to the decorator, I said, hey, there's a problem here. He says, well, what's that? I said, you only painted a third of the wall. And he said, well, that's all I could do. So that's the same analogy in terms of painting the inflammatory wallpaper. Why would you use a formulation which is only going to reach the proximal airways when you can use a formulation which can reach the whole lung? So I almost exclusively now, to answer your question, I can't see why you would ever use a coarse particle formulation if you have a small particle formulation or an extra fine, call it what you want, of the same class of drug. It makes no sense at all. What I would say that to date, the evidence is better in asthma for extra fine particle formulations than it is in COPD. But by the time I get my next research fellow in Q3, Q4, then we might also have the answer in COPD as well, because that's the project that we're attempting to do.
Excellent. Very quick answers, Brian, because we are falling a little short of time. There are 4 questions that I think are very, very important. Can you differentiate between the 2 phenotypes of COPD, the chronic bronchitic phenotype and the emphysematous phenotype, using the AOS?
You can to a degree, in that the emphysematous phenotype will have a disproportionate increase in AX compared to R5. Okay, there'll be a much greater discordance in the emphysematous phenotype than in the chronic bronchitis phenotype. You can actually, to be honest with you though, you can get that information with a stethoscope just by listening to the chest, and the emphysematous phenotype will have poor air entry, so you probably don't need an impulse oscillometer to tell you that.
Can you differentiate between asthma and COPD using this AOS?
Can you just, no, you can't really, because you could have, here's the dilemma for me in the clinic, is we have very heavy smokers who are smoking asthmatics, yeah, and how would you differentiate that from a COPD? I think that's the germane question here. And the answer is really, it's very difficult. If someone smoked all their life, they may well have had an asthma phenotype, and they're a smoking asthmatic with type 2 inflammation, or they could have COPD and have type 2 inflammation. But to be honest with you, it doesn't really interest me, because at the end of the day, whether you're a smoking asthmatic or whether you're a smoker with COPD, what determines the response to treatment, and particularly inhaled steroids, is whether you've got the type 2 phenotype in terms of having a peripheral blood eosinophil count more than 300 cells per microliter. That's what determines whether you're going to have reduced exacerbations in response to taking inhaled corticosteroids. So I don't really care. So what really matters is whether you've got high eosinophils, and B, whether you're a frequent exacerbator.
So 2 more questions, Brian. I think we're falling just short of time. Are there reference values for AOS? Do you need to generate the reference values for each individual region or country? In your presentation, I did not see percentage predicted values for R5 minus R20 or the AX. You use absolute values. So do you believe that there are absolute cutoff values, single cutoff values that differentiate between normal and abnormal, unlike what we do with spirometry, where we tend to use the percentage predicted values to differentiate between normal and abnormal?
Well, the machines, the Thoracis Tremorflow and the Jaeger Master Screen will give you percent predicted values. But to be honest with you, I don't find them particularly useful. And in any case, when I'm seeing patients, what's more important to me is the change or in response to intervention between subsequent clinic visits. That's what's important, okay? So it's the within subject change. But here's my rule of thumb, which is what I published in the Lancet in 2014, is that my rule of thumb is if your total error resistance, R5, is more than 0.5 kilopascals per liter per second, yeah, which is 5 centimeters of water, multiply it by 10. To me, that means it's abnormal. If your I5, R20, this is in adults, not kids, because kids have higher values. In adults, if your R5, R20, excuse me, is greater than 0.1 kilopascal per liter per second, which is 1 centimeters of water, that is abnormal. And in adults, if your AX is more than 1 kilopascal per liter, which is 10 centimeters of water per liter, that is abnormal as well. So those are the numbers that I keep in my mind when I'm in the clinic. And then also, we then serially plot on the computer the differences in response to interventions when we're treating patients in a clinic, whether it be changing formulation to an extra fine or whether we're using biologics.
You know, Brian, what this reminds me of is for spirometry, you need to have the age, gender, height, ethnicity. Unlike what we do for blood pressure or for blood sugar, what you're telling me is using fixed cutoff values, like how do we differentiate between hypertension or high blood sugar for diabetes? You know, this I think simplifies the way you treat you make an interpretation of the report. Unlike spirometry, where so much of it depends on so many factors, whereas I believe airway oscillometry gives you just like the cutoff values like you have for hypertension. Above that is abnormal, below that is normal. I think that's going to simplify a lot of clinical practice if what you're saying is true.
That's a good point. Yeah, I like the way you put that, actually.
Yeah, the last question, Brian. Is there a role for AOS in interstitial lung disease?
Yes, there is. Yeah,
can you help diagnose? Can you help follow up these cases to look at response to therapy?
Well, it's not as well established as measuring spirometry or static lung volumes in ILD. There's not as much data out there, not the same density of literature, but there's no question that if you do serially follow patients with IPF, then you can see changes in lung compliance. The main one to follow in IPF, obviously resistance doesn't change, that's a given. So the main one to follow would be AX. That's the one with the best signal to noise ratio. However, what we don't have is all of the pivotal studies, like with nintedanib and pirfenidone, they followed forced vital capacity. So there's no serial evaluation from large-scale randomized controlled trials with either AOS or IOS. But yes, you can certainly detect impressive changes in AX. In fact, to a much greater degree than you can with forced vital capacities when you're following patients with IPF or any ILD, whether it be sarcoid or hypersensitive pneumonitis. Yeah.
I think with this, Brian, we would come to the end of this wonderful webinar. I think these are exciting times ahead. What you have presented is very futuristic, is an instrument that gives you a lot more information than what spirometry does. It does not generate any aerosol. So in the COVID times, it would perhaps be the most important diagnostic test that you can use in a clinic. A simple test that does not require any effort from the patient's point of view. By and large, I think it also gives you additional information than what spirometry does. So I'm very excited about this. And I think the future of the future in the chest clinic for a respiratory physician is going to be, I think, much greater than what we had today. Thank you for an absolutely excellent presentation. As always, it's a pleasure to listen to you, and there's so much to learn from you. Thank you very much. Professor Brian Lipworth for this wonderful day. I would like to express my very sincere thanks to Thorasis and Schiller for having supported this event, and the Indian Chess Society for having accredited this very important educational activity. So with this, we would come to an end. Thank you very much to all the delegates who have joined us today. And I hope that today's presentation is going to be a game changer for many of us who practice respiratory medicine. So with this, thank you very much, and good night. Have a wonderful weekend ahead.
Can I just say one thing, is that
Please.
I write a regular blog on respiratory medicine in LinkedIn. So before you go, if you want to scan the QR code in the top corner, that will take you directly to the LinkedIn site, and you might find that blog of interest. If you want
excellent. So I think we would hold that on for a few seconds, but I'm sure a lot of us would directly go to your LinkedIn website, to your LinkedIn site, Brian. Thank you very much. And so with this, we conclude, and I hope, Brian, that we get to see each other at some point of time soon, and hope that you can come to India to share your more knowledge that you would have earned in this very exciting field. Thank you, and good night.
Take care all. Stay safe. Bye then.